Okay, sounds great. So today I'm going to introduce to you project 2. I released it just a few minutes ago. I was testing it on Delta to make sure that everything is running smoothly. There were some hiccups, but finally it worked out pretty well. So it should be fine if you want to test it on Delta now. Okay, so let me share with you my desktop. Okay, so first we have your course canvas. It is again a reminder for the students who just joined us. On Wednesday, we are going to have exam 1. Last week, I posted the study guide and also some sample questions on announcements. You can also find some more instructions about exam 1, the modality and the materials that you're allowed and you're not allowed to bring to the exam. And I hope everything goes well with the exam. Don't forget that you can have a cheat sheet, one side of a letter size paper. So you can take advantage of that, whatever equation or formula or definitions that you think might be a little tricky for you. You can write it on that piece of paper. And then by the end of the exam, your TA will collect all of those cheat sheets from you in addition to your answer sheets, okay? That's pretty much it about the exam. And then today I'm going to mainly focus on project 2, which I released just before the meeting. So the main page is the project file. So I posted the PDF file, and this is a brief introduction about the project. This is a group project, so I just expect to receive 1 submission per group, and it's due by March 11th. So you have about 3 weeks to complete this project. In addition to that, I have posted some other materials here. I'm going to go over that during this presentation, but just for your information, the first supplementary information is a Unix shell for beginners. So if you are not very comfortable with command lines, a Unix shell, I think this is a great introduction to you. It also has some more advanced commands. So if you are comfortable with what is taught here, you can skip it and look at shell extras, which has some additional command lines. This is not necessarily needed for project 2, but I hope that in this course you get to really hone your computational skills, and particularly your command line and Unix shell skills, because those are very essential for high performance computing. Okay, so I shared with you this link on Canvas, and then in addition to that, we have a file. It's an MPI code for running pi estimation in parallel. Okay, so I'm gonna explain to you why it's needed, but these are the 2 supplementary materials that we have on this module. Okay, so with that, let's get started with what we have in the project description. So if you just simply download the PDF file, you can follow what I'm going to explain today. I hope you also have your terminal and your VS Code ready, because we're going to do some live coding as well. Before that, let me check my chat box. Does anyone have any problem with my voice? Is it breaking, or is it just one student who had a problem? Can you hear me fine? Okay. Okay, so let's continue. Okay, so here is project 2. It's about estimating the value of pi. I highly recommend you to watch the video that I posted last week on Monte Carlo simulation. Recall that last week we had a hybrid meeting, and I decided to record that video. That works as the main reference for Monte Carlo simulation. I explained to you what are the first definitions and concepts, and we looked at one example together on, it was actually the finite integral. So we worked on that example together to see how we can estimate that integral using Monte Carlo simulation. So definitely take a look at that before maybe starting this project, because here we are assuming that you know the basics of the Monte Carlo simulation, okay? So this is a very brief reminder of how it works. In Monte Carlo simulation, we basically generate thousands of, usually in that order of magnitude, of random numbers, and they help us with estimating some pretty complex, mathematical values. Here we are mainly focusing on estimating the value of pi. We all know that pi is around 3.14. But this, it's an irrational number, and therefore this, I know after this point we have so many digits, and there is not a regular pattern for that. And there are different methods for estimating the value of pi. And today we are going to use Monte Carlo simulation to estimate it more accurately. Okay. That's, the gist of it. And in addition to practicing Monte Carlo simulation, we are also going to see how, a piece of code can be executed in the serial version and also in a parallel version. This is not a parallel computation class, so I don't really expect you to convert a serial code to a parallel code. I have given you those pieces of codes. But we are going to run them on Delta to see how they work. And then towards the end, I have for you the project deliverable. Similar to the previous project, you are expected to explain what's going on here, and then you're going to run some experiments in order to draw a graph and then compare some numbers. Okay, so I have almost everything for you here, but let's start from the beginning to introduce the problem more clearly, and I'm going to go over all the steps with you to make sure that we're all on the same page. Okay, so this is a brief introduction to Monte Carlo simulation. We know that it's a problem-solving strategy which uses statistics and random number generation. We usually deal with a probability in Monte Carlo simulation, which is, calculated by, by definition, is the number of event occurrences divided by the total number of simulations or your sample size. So when you generate some random numbers, you get to calculate or estimate this probability, and that's what you need for your final calculation. So in this case, we are particularly interested in the approximation of pi, which is a mathematical constant. I'm sure you're all familiar with that. And it shows a relationship between the length of the circumference and of a circle and its diameter, right? So if you have the circumference of, let me admit two other students. Okay. So if you have the circumference of a circle as C, then it's equal to D, which is the diameter of the circle multiplied by P. You may remember it as C equals 2R multiplied by pi, because R is the your radius, so 2R equals to D, which is your diameter. So whatever you're more comfortable with, that is fine. But basically it's relating the length of the diameter of a circle to its circumference. That's pretty much it. As I mentioned, we all know that it's around 3.14, but it's just a simplification of this number. It is an irrational number, so the numbers after the floating point, goes on, and depending on the accuracy of your calculations, you might be interested in different, digits after the floating point. So the question here is that how we can use a random number generator algorithms in order to estimate pi. So we need to have a strategy to relate the value of pi to something that we already know. Okay. So what we are doing here is to put or inscribe a circle inside a square. And here what we are doing is to just look at a quarter of its area. So you have this big circle, and we just inscribed a quarter of it inside a square. And then we want to know how this can be calculated. I'm a little here. I have length of 2. Okay. Okay, let's check the numbers. It might be a little tricky here, but because when I was looking at the numbers, to me, it should be a little different, but let's work on it together. Okay, so let's assume that the circle has a radius of 1, and that's what I think the length should be 1. 2 is not correct here, because if the radius is 1, then the length of the square here should be 1 as well. So I think I need to edit this number. It doesn't look correct to me. I believe I copied it from the textbook, but I don't know, it might be a typo. Anyhow, so if you have the circle of radius 1, let's assume that you inscribed it in a circle with length 1, right? So then we are going to have something similar to this. The yellow area is showing, the area of the circle, and then the blue one is what is left in that square, right? So the area of the square is 1, right? So if the length of the square is 1, again, forget about this 2, it should be 1. Then, that by the definition, the area of the square will be 1. And then the area of, the circle is PR squared, right? So PR squared is, or pi r squared is pi if the radius is 1. But since we just have a quarter of it, then the area of the yellow part will be pi divided by 4, right? So the area of the yellow part is pi divided by 4. The area of the whole square is 1. And now we want to relate these two by using random numbers and Monte Carlo simulation. Okay, so what we can say here is that if I start, generating some random numbers in this rectangle, similar to what we did for, calculating integral last week, then, some of those numbers may lie into this yellow area, and some of them might be outside the circle, right? That's, what we expect. And if we do this over and over and over again, then we can have a good understanding about what fraction of the main square is allocated by, this quarter of the circle. And that helps us with estimating pi. That's basically the main idea. Okay, so what you see here is that, the way that I was explaining this to myself was a little different. So maybe that helps with understanding it better. So if you have, the main square here, again, we know that the area of the square is 1 if the length of each side is 1. So the area of the square is 1. And the area of this quarter of the circle will be pi divided by 4. We just reviewed that together. Okay, so that, you know, should be equal to m divided by n, where m is the number of randomly generated numbers that are inside the yellow part, and then n is the total number of points that are generated. Okay, so this is, how it's calculated, and I would say that this is an approximation, right? Because you need to have a very, very big number of random numbers in order to, confidently say that these two are equal. But since we usually have limited resources, then it's somehow an approximation of pi. Okay. So basically, that's what we're doing. We are going to generate thousands of random numbers, and then we are going to see how many of them are inside the square and how many are not. And with that, we can estimate the value of pi. And this is the main equation that we are using for that. This is the underlying math. I think it's really great to understand how it works. And, I definitely encourage you to work on it with your team members. However, when it comes to implementation, you don't necessarily need the every details of it because you currently have the implementation in Python. So that's, the idea. Any questions about the idea for calculating for estimating pi using Monte Carlo simulation? Is that clear to everyone? I'm gonna wait here for maybe a minute to make sure that we're all on the same page. Any questions about the problem statement? And sorry for this typo, I'm gonna fix it, but that shouldn't be a very big deal. I try to explain this equation without that typo. Okay, I hope that it would be clear to everyone what we're going to do. But with that, let's focus on the implementation of the algorithm. Okay. So according to what I explained, we need to generate a lot of random numbers in order to estimate this fraction of the circle, and accordingly estimate the value of pi. You can do this in two different ways. Apparently, you can just simply generate thousands of random numbers, and there is no problem with that. However, this is a very interesting problem that could be executed in parallel, because when you are generating random numbers and you are, seeing whether those numbers are inside the circle or not, these tasks can be done independently, right? There is no reason for you to wait and see what was the results for, random number, for example, index I, before starting the generation of random number index I plus 1, right? You can run these tasks in parallel. There is no dependency between them. And that's why we can save some time if we have enough resources to run multiple threads in order to complete the job. Okay, that's the main idea behind parallel computation. So if you have a job that is made of smaller tasks, and you can break it down into simpler tasks such that they are executed on different threads without any dependencies, then you can have a parallel job. I remember when I was a student, I took two courses in parallel computation. One was, basic parallel computation, and the other one was the advanced one. So there are many cases where you do have some dependencies between the tasks, and there are some strategies to deal with those cases. And assigning different tasks to different threads can be pretty challenging because it also leads to some overhead. Basically, when you are breaking down the main job into smaller tasks and then you're assigning them to different CPUs, and then you want to collect the answers and put them together, you are adding some overhead to your simulations. And then the main question is to what extent you want to break down the tasks into smaller jobs, and then how many threads or cores do you want to employ in order to have the most efficient implementation of the algorithm. So that's, another area which is very interesting, but not completely what we want to do for this project. This is just a very brief introduction to what parallel computation is. And if you are interested, we can, talk about more advanced projects as, something you can do in addition to this project. But for now, this is the idea of parallel computation and a single thread versus multiple thread execution. Is this clear to everyone? Okay. You can, if you have any questions, you can either type it in the chat box or you can mute yourself. I want to make sure that I'm not just talking to myself and you're following me. So a little feedback from you will be appreciated. Okay, so let me move on to the next page. What I just explained is also, described here, how we can break the main job into smaller pieces, and why Monte Carlo calculations are very popular in parallel computation, because, based on the definition of this simulation, you're dealing with some independent random number generation tasks, so you can, assign them to different threads. Okay, so in Python specifically, we have a library called MPI for Pi, and that allows us to implement and run jobs in parallel. Okay. MPI stands for Message Passing Interface. And that is, a very popular method for parallel computation. And the way it works is that once you define the main job and the smaller, the main job, and you make sure that there is no dependency between them, then you are going to have a master process, which is a rank 0 processor. And then you have the other processors or processes, right? So the master's job is to assign smaller tasks to the other processors. This is also called master-slave paradigm. So the master assigns those smaller tasks to the other processes, and then they, run their job, they finish, the calculation, and then the master, collects all the results from the processors. They put all the processes together, and then outputs for you what is required in the main project. So in this case, what we want the master process to do is to, ask each processor to generate, points, and then compute distances, and, see whether the generated points are inside or outside the circle. And with that, we can put everything together in order to display the summary and estimate pi. I'm going to elaborate on that once I show you the code, but this is the main idea behind, parallel computation. Okay, I'm going to pause here a little bit to make sure that it's clear to you. I guess if you compare these two figures, it should be, pretty straightforward what we are doing. In MPI, we just simply assign each task to one processor, and that is done by master by the master processor, which is ranked 0. Okay. No questions. We're good. Okay, so let's move on to our project. So far, it was mainly about introduction and some new definitions, but now let's see what we have for this project. So far, you have finished project 1 and you're familiar with Delta and how to communicate with that, how to run some jobs on it. And therefore, I'm not going to go over all the steps that I have here for you today, because I think now you are able to follow the instructions. I'm just going to share, the most important parts with you. And therefore, I'm gonna wait for you to follow these instructions, but I try to avoid, going through all the details, because I think you have developed some skills now and you are able to do that on your own. Okay. So the first part is to downloading some files that we need for running the simulation. One file is simulating underscore pi.py, which can be found on the on chapter 4 of your textbook. Okay, so if you go to your the GitHub repo of the textbook, chapter 4 has a Python code called simulating underscore pi.py, and that is basically the implementation of what I explained to you earlier. Here you see this pi equals 4 multiplied by m divided by n. This is exactly what we have here, and this is how we estimate pi, right? So if you're interested, it does some plotting for you. So if you like, on your local machine or on Chem Compute, you can look at what it basically does. So I have the code on Chem Compute, and again, recall that you cannot run it directly. You need to create a Jupyter notebook in order to run it on Chem Compute. So let's take a look at this serial code together, and make sure that we all understand how it works. So let me create a Jupyter notebook. If you have everything on your local computer, such as such as what I have here, you can just simply run it. It should be running smoothly, and it should generate for you a plot like this. If you don't have it on your computer, you don't have VS Code, or you're facing some problems on Chem Compute also, you can, sorry for switching between different windows, you can just simply copy this block of code and run it. So this time we are using their resources to run the code, and it generates for you a similar plot. Okay, I'm gonna wait here for a couple of minutes to make sure that you can run the serial code successfully and you're not facing any problems. If you finished running the code, I don't know, you can type finished or done or successful, something like that on the chat box, so I can, monitor how it's going on your end. Okay. See some people who could run it successfully. Good job. This is great. If you are interested, you can change the number of points that are generated in the code and see how it affects the visualization. If you go with fewer points, you would expect more white regions here because you are not really covering the entire area. If you go with more numbers, you will get to see solid yellow and solid blue and the plot. Okay, that's great. We have a good number of done messages on the chat box. So I'm going to continue with project 2. Okay, so that was what the serial code that we have in from the book. And what I want you to do is to change one line in the code. So if you look at the code on line 27, you see that when it shows the estimation of the pi value, the precision is 2 floating points. But for our simulation, we want to increase that number to 10. Okay, so on your local computer or on ChemCompute, just change this number. And then I want you to download the edited code and put it on your desktop. Okay, so on your desktop, you should have the serial version with a modified line of code, which generates for you more precise numbers. That shouldn't be very hard. Just put it on your desktop because later all the paths that I have for you are from your desktop. So make sure that they're on your desktop. In addition to that, I want you to download the MPI implementation of the similar problem from Canvas. So if you go to wk4, so here I am on the course Canvas. If I go to modules, then there is wk4 and there is project 2 MPI code. Here you can find the parallel implementation of the similar code. I want you to download and move it to your desktop. Okay, it should be pretty straightforward. I have both codes on my desktop, the edited simulating underline pi, which is the serial version, and also the parallel version. They're all available. They're both available on my desktop. Okay, so from here, I have some instructions for you to transfer these 2 files to your account on Delta. Okay, so let's also do this together. I'm gonna, stop right before project description. I believe this is the part that you should be working on with your team members, but let's make sure that you can transfer the file successfully and you can run a simple job on Delta successfully. Okay, so with that, let's start the warm-up activity. I want you to open a terminal and log into your account on Delta. I'm going to do that now. So this is my terminal. I am going to SSH to my account at login.delta.ncsa.illinois.edu. You just need to copy and paste this piece of code on your terminal, and instead of access_username, type your username, okay? So you try that, it asks for your password, it doesn't show the password that you're typing, so feel safe to do that. Then I want you to open your due push application. There should be NCSA in there, so open that. The passcode might have been expired, so refresh your passcode and then type it here. What you see on your cell phone is definitely, most likely different from what I have. So this passcode may not work for you. Type what you see on your own cell phone. Okay, I'm gonna pause here for a couple of minutes to make sure that a good number of you could connect to Delta. If you could do that, type something like connected or logged in or I don't know, done, something like that. Okay. That's great. Perfect. You should see this delta sign to make sure that you could log in successfully. Okay. Gonna wait a few more seconds, maybe a few more confirmations before going to the next part. Okay, that's great. And with that, let's follow the instructions that we have here. Okay, so what I want you to do is to create a new directory on your account there. So I just copy this part. I'm making a new directory called project 2. If I want to make sure that it's created, I just type ls. You might not have the other directories that I have, which is totally fine, but you should see project 2 there, meaning that the directory has been created successfully. Then I want you to cd to project 2. Okay, so you're changing directory and you're going to project 2. And if you ls here, apparently there is nothing here, you just created the directory. Okay, so from here, I want you to be careful about what I'm explaining because we are going to change the terminal. Okay, so this terminal is currently showing what's going on with my account on Delta. I want you to open a new terminal. You can either open a new tab. So on my Mac, what I have is Shell. There is new tab. You can also try new window. Either would work. On your computer, if you're using a Linux machine or a Windows machine, it might be a little different, but I just want you to open a new terminal, okay? By default, it shows your personal computer. Okay, thank you, Sergio. So you just open a new terminal. And for me, this is what I have, right? So I opened a new tab, and that is on my local computer. The other one, though, is on Delta. Okay. Okay, now that I'm on the other terminal on my local computer, I want you to go to your desktop in order to find those 2 pieces of Python code that we downloaded. Can you tell me how I can navigate to my desktop?
CD desktop.
CD desktop, right? So I'm currently on my home directory, right? If I ls, I can see my desktop here. So from here, I just cd or change directory space desktop. Recall that you can press tab and it fills out for you the remaining part of the word. Now that I'm on desktop, I can do ls. If I do lt-lt, it lists for me all the files in the reverse, sorted based off of the time that I either created or changed them, right? So the two Python codes that we talked about should be on the top of the list because I just worked on them. So let me see. Yes, so I have simulating underscore pi, and I also have estimate underscore pi underline parallel underscore parallel dot pi. These are all the other stuff that I have on my desktop. Apparently you don't have them, but you should find these two files on your desktop. Okay, so from here we want to transfer them to Delta, and let's do that one by one. So I have for you two SCP commands for transferring the files. So the first one is transferring simulating underscore pi, which is the serial implementation. And the second one is transferring the parallel implementation. Let's copy the first one on the terminal, which shows your desktop. Okay. So, oops, didn't I copy it? Okay, so I have to edit it a little bit. I need to replace this part with my username on Delta, right? Then I press enter. It asks for my password on Delta. I type it. Again, I have to enter my passcode. Good practice is to update it because it might have been expired. Okay, so you should see something similar to this. 100% means the file has been transferred successfully. And we are going to repeat something similar to transfer the other file. So I'm going to copy this part, paste it here. I need to edit this part of the command. Typing my password and the passcode. And transfers the file. You could do this together. In fact, you don't really need to repeat SCP twice, but I thought it's more straightforward this way, and this is what we have in the file, but you can avoid this extra step and transfer them together. But anyhow, it seems that everything went pretty well, so I'm switching back to my terminal on Delta, and recall that we are now in project 2. If I ls here, I should see the two files that I just transferred to my account on Delta. And this is a confirmation showing that the files are there and everything is fine. I want you to check that. And if you could transfer the files to Delta successfully, let me know. Sergio, I just saw your message on chat box. Are you referring to the SCP command? If so,
Yeah, sorry, can I see the command to bring the files from the desktop to Delta? I had
yes,
to go AFK for a second.
yes. So I'm actually copying and pasting the commands from this PDF file, which I downloaded from Canvas, right? So you have this file in there, but if you want, this is what I copied and pasted from that file. So for the first file transfer, I had SCP, and this is the serial code. And then for the second one, again, I had SCP, but this time I had the parallel implementation. Make sure
Okay.
that you're on your desktop because the two files are on your desktop. So you need to first CD to your desktop, ls, and make sure that the files are in there, and then you can transfer the files.
Okay, thank you.
Okay. Okay, if you are on your Delta account in project 2, do ls and let me know if you see the two files in your directory. I'm gonna pause here for a few minutes to make sure that it could transfer the file successfully. Oh, that's great, Paul. If you're receiving any error messages, if something is not clear for you, let me know. Without transferring the files, we cannot do anything. So I'm gonna wait here for a few minutes to make sure that we're all on the same page, or at least a good number of us are on the same page. Oh, perfect, Kevin. That's great. Okay, while I'm waiting for the other students to transfer the files, for those who could do this successfully, recall that there are different editors on Linux, and one of them is Vim or VI. There are other ones like Emacs, but I'm more comfortable with Vim. So you can open these files with Vim and take a look at what we have in there. Okay, so the serial implementation is the one that we borrowed from the textbook, right? So this is what we have in there. There are some libraries that are importing first, and then we generate some random numbers by using the random module in Python, and based off of the equation that I showed you in the PDF file, we're approximating the value of pi, and then we do some plotting here, but since we are on that cluster, plotting is a little tricky, so we don't really get to see what it does. We just work with the numbers that it generates. It does generate for us the estimated value of pi, so we can look at the output files that way. We can also open the other file, estimate, whatever, the parallel version. So you can see that it's a little different. First of all, we are importing mpi4.py, the one that I explained to you in the PDF file, and that allows us for running the parallel implementation. And there are some new things here that are a little different from what we had before, right? We're working with ranks. So recall that rank 0 is your master, which is basically breaking down the main tasks and also collecting the results from the other processors. And the other ranked processors are, working on smaller tasks, which are generating random numbers and then seeing whether they are inside or outside the circle. The code that I shared with you, the parallel version, is not exactly the parallel version of that serial code. I mean, if you compare the syntax, you see that they are a little different, not the parallel part, but also just like the definitions are a little different. That's because I borrowed the implementations from two different resources. So the syntax are a little different. If you are very interested in parallel computation, and if you want to challenge yourself, what you can do is to start working with, the serial version, which is simulating the underlying pi.py, and try to convert it to a parallel code using MPI. you do have, a sample code in, estimate underscore pi underscore parallel. So that helps you as, a big hint. You can also Google, NPI commands to see how you can do this. This is not needed for this project. This is completely extra, but I think, it's really exciting to see how you can start from a serial code and then change it to a parallel code as a practice. So that's something you can do, but for this project, again, it's not necessary since we already have 2 implementations, so we can, continue that. Okay, I see some of you had some problems with, oh, okay. So Sanskar, I see it seems that that directory has not been created, project 2. You don't need to be in that directory. If it's created successfully, then it should be working. So maybe, I don't know, wait after the class and we can try to fix it. I also see that Sergio, you have a problem, so maybe you wait after the class and we can work on it, okay? But for now, I'm going to show you, okay, that's great, Sergio. I'm trying to show you how to run the job, and that should be very helpful for you in order to start the project. Again, I'm gonna stop after project description. That's what you are going to do with your teammates. I wanna make sure that you can run the basic jobs. Okay, now that we have transferred the files, we can see them in project 2. We are going to open an interactive session in order to run our job. Just few minutes before the start of the class, I tried to, open a new session with 64 CPUs. It didn't allow me to do that. It took me forever, and then it just it didn't work. I guess that they are running some heavy jobs on Delta or something like that. We can try it now, and this is definitely what you need to do later when you want to fill out this table, because at some point you want to run it on 64 CPUs. So let's try this command, but chances are that it doesn't work, and then we need to reduce the number of tasks per node in order to ask for smaller computational resources. Okay, so we don't need that terminal on our local computer anymore. I'm going to close it to make sure that there is no confusion about that. So the only thing that we have is our terminal on Delta, and that should be fine. Okay, so oops, okay. Okay, so if you just simply copy and paste it from here, you may see that there are some enters between the lines. So you may need to type some part of it, or maybe copy that that part of the PDF file in your notebook or something like that, and then paste it here. I believe that I have the commands in I have them in my history, so I'm just pulling it here. If I go with 64, again, I doubt that if it will let me to get it. It waited forever and it didn't really give me the resources. So what I'm going to do now is to ask for fewer number of processors. And for doing that, you need to change 64 to, let's go with 4 for now. And that should be allocated pretty quickly. Okay. So for me, it's done. I don't know why it gives me this error. This should be something relevant to their own setting. Don't worry about that. But once the interactive job starts, you get to see this. So instead of login node, now you should be on a GPU node. Make sure that you are on a GPU node, not necessarily B25. Where I am, you might be on some different different compute nodes, but this shows a kind of confirmation that you are on a compute node. And then from here, you can run your jobs, without any worries, because if you are on a login node and if you run a heavy job, then they terminate your job, and chances are that they send you an email and give you warning that you can't run jobs on login nodes. But when you are on a compute node, then you're fine. You can run whatever you want. Okay, let's go back to this PDF file. Again, what I did was to change the number of nodes to 4 in order to make sure that it's allocated pretty quickly to me. From here, I need to load Python. And this command module is what we have in the workload manager, right? So it lets us deal with, load and unload the modules that we need. So if I do module list, now I get to see what modules are loaded. I have some compilers here, and the very last module is Python 3.7.17, which was loaded based off of the command that I have here. I believe they have different versions of Python, but this is their default version. And since I didn't determine the version, they just went with the default version. Okay, now that Python has been loaded on my account, I can move on to the next part, which is about running the serial version. Okay, so with the serial version, you just simply call Python and your code, and then you compile it. It may take some time. I think it generates, yes, it generated for me 10,000 random numbers, and then M and N values that we had in the PDF file. This is what we have. So 7,840 of those numbers are, let me see, M was inside the circle, right? Based on this definition. Yes, so this number of the total generated numbers are inside the circle, and this is its estimation of pi using Monte Carlo simulation. This is pretty accurate. We're not that far, but in the next exercises, when we have more number of randomly generated numbers, you see that this number gets more and more accurate. Okay, now what I want you to do is to run the parallel job, okay? So let's go back here. So this is a sample output that I had. You see this one is different from the other one because I didn't fix the seed. So whenever that I run it, I get to see some different random numbers, and therefore this could be different on your computer. Oh, Wilson asked how we quit the queue. You just press Control and C. Okay, sure. Okay, now we want to run the job in parallel. So I'm copying this part. Be careful that you cannot run it directly because you have to change this capital N, okay? So let's see what we have. This time for running the parallel code, I'm calling MPI run first. By default, OpenMPI is loaded on Delta, so I don't need to load anything else. And I just loaded Python, so that is also fine. -MP determines the number of processors. Since on my job allocation request, I asked just up to 4. I cannot go above that. Let's just go with 2 for now to see, how it works. And then later in that project, you are asked to go up to 64. But for now, let's try 2. So I'm employing 2 processors in order to generate random numbers and then estimate the value of pi. It takes some time because I believe in the parallel code, we are generating 10 million number of random numbers. Okay, so you get to see a bunch of lines here. It's telling you that, it was successfully running, so that's great. And then this is the allocation node. What is important and you need for your report is this line. Okay, so what it's saying is the estimation of the of pi, right? And then this also shows the standard deviation. We don't necessarily need it now, but I'm sure you know what standard deviation is based off of the topics that we had earlier. You can ignore some of these things, but basically what we need here is that there are 10 million sample points in the code. We used 2 processors for running this job. It took us 20 seconds for running the job, and this is the estimation of pi using that piece of code. Okay, so that's pretty much it. That's what I want you to do. I don't need you to change anything in the parallel code. You see that here the number of samples is 10 million. I don't want you to change it at all. What we are going to do is to see how having more and more number of processors improves or maybe makes it less efficient when it comes to the estimation of pi. So that's for that part. And then I want you that in the serial code, I want you to change the number of sample points from 1,000 to 100,000 to see how it affects the accuracy. And prior to that, I want you to explain what's going on in the code. So line by line, analyze the serial version and tell me what's going on in there. Sorry, I explained everything in the reverse order, right? So I started from number 3 and I went up to number 1, but that's pretty much it. I want you to work on this project together, maybe after taking the exam. For now, maybe you just focus on exam 1, but this is what you have for project 2. This is your deliverable. I'm gonna fix this little typo here and post the modified version on Canvas to make sure that everything is okay. But that's pretty much it. For those of you who wants to challenge yourself, you can compare the serial and parallel implementation of the code. As I mentioned earlier, I borrowed them from 2 different resources. So the parallel version, estimated underscore pi underscore parallel, is not exactly the parallel version of what you see here. There are different syntaxes and different variables that it's using. So one best way for practicing parallel computation is to start from a serial code and then change it to a parallel code. If you want to challenge yourself, we can do that. Otherwise, you just follow the instructions that we have in the project description, and then the deadline is March 11 for final submission. Okay, that's all I have for today. Okay, I see some of you are receiving some errors on Delta, so I'm going to stay here for a few more minutes. If you have any questions, I am also going to hold my online office hours right after the class. It's a different link. So it's your preference. If you want to stay here, just stay here. Otherwise, you can go to the other Zoom link to meet me at 3:15. But that's pretty much it from me. If you don't have any questions, you can leave this meeting. If you have any questions, you can stay in the room. I'm going to stop recording, and I wish you a great exam on Wednesday. I hope everything goes well.